The first configuration that we're going to consider is our common-emitter amplifier. And so we're actually going to spend a lot of time looking at variations of the configuration you see below before we get to our common collector and our common base configurations. So we're going to start by looking at this simple example here where we have our voltage divider biasing with R1 and R2. We see we have a collector resistor RC, and we notice that our emitter is at ground. So because this emitter is connected to our ground, that's where we get the name common emitter. We also have this small signal input V of S over here, which is connected to the rest of our circuit via this coupling capacitor CC. And so before we take a look at the small signal equivalent circuit, I want to make a quick note about that coupling capacitor. So we've kind of already touched on this a little before, but our coupling capacitor, or really any capacitor, is going to have an impedance of negative J over omega C. And in this unit, and for our MOSFET amplifiers as well, we're going to be considering that we have frequencies that are in a mid-frequency range, or sometimes, I believe in the textbook, it will also call this mid-band frequencies. And so what does that mean when I say mid-frequency? That's a very vague term. It doesn't really give us a whole lot of information. Well, there's two things. We're going to assume that our frequency is large enough so that Z sub CC is going to be negligible for our AC signals. Large enough so our Z CC is negligible. But at the same time, we want it to be small enough, the frequency, such that our parasitic capacitances in the BJT can be neglected as well. So parasitic capacitances, so in our BJT can be neglected. And so that's not something that we're really going to go into a lot of detail. But basically, if we were to take a closer look at our BJT structure, of course, in this case, we have an N region, a P region, and an N region. It turns out that there's some parasitic capacitances that result as sort of the interaction of those regions, and it turns out that they're frequency dependent, just like any other capacitance. So we're talking about frequencies sort of between those two limits, and again, you'll notice I'm not necessarily writing a hard range of numbers, and that's because it's going to depend a lot on what frequency signals we're dealing with. Of course, we can adjust this coupling capacitor, so that's going to adjust what is large enough so that that's negligible. For different BJT models, these parasitic capacitances are going to change such that what's small enough is going to be defined differently. So because of that, we can't have sort of a hard and fast definition of, the frequency has to be between 5 kHz and 600 kHz to be mid-frequency range. But in general, we do want to be at least on the order of kHz, usually around tens of kHz. And then once we start getting up into megahertz range, then we're starting to get closer to our high frequency range. So just sort of as a really general rule, we can think about kHz up to hundreds of kHz and maybe a little bit into megahertz when we're talking about this mid-frequency range. But again, of course, we can select different capacitor values and different BJTs depending on our application. Ultimately, though, what we're going to do when we're working on our analysis in this book is we're going to assume that for our DC signals, that our capacitor behaves like an open circuit or looks like an open circuit. So caps look like an open circuit. And then for any AC signals, we're going to assume that the caps are looking like or behaving like a short circuit. And so, of course, if we want more accuracy with that, we can go to a simulation or we could refine our model a little bit. But for this class, we're just going to stick with that. Okay, so with that sort of intro out of the way, let's return to this specific circuit and let's see if we can figure out our small signal voltage gain. So we have some input voltage Vs. I've defined some output voltage here, and so this is at the collector. And so in our summary table at the end, I'm going to specify sort of all the things that make this common emitter circuit a common emitter. So for instance, like I've already mentioned, we have our emitter at ground. By definition, we also have our output off the collector, and we have our input signal connected to our base. Okay, so what we want to do then is we want to construct our small signal equivalent circuit. So let's start there. And what we're going to see is that it's going to be easier if we start by doing our hybrid pi model for our BJT. So over here we have our collector terminal, here's our base terminal, and here's our emitter terminal. So let's start with that, and then we're going to connect all of these external components to sort of fully realize our circuit. So let's come down here, and let's start by labeling our base, our collector, and our emitter. And so from our previous work with hybrid pi, we know that we have this R pi resistor between our base and the emitter. So this is R pi with some voltage V pi across it between our collector and the emitter. And so let me actually move this over a little bit because we're going to go ahead and include our small signal output resistance for completeness. So we have something that looks like this. We have a dependent current source going from the collector to emitter. And so this has a value of beta IB. And then we also have this small signal output resistor R0. And so that's due to our early effect. Okay, so this is what our transistor can be modeled as. So now what we want to do is add the other components from our circuit. So we come back up here and we can say, well, from our collector, we also have this resistor RC, which is connected to VCC, but remember we deactivate DC sources, so that's going to be at signal ground. We can see that our emitter is just directly connected to ground. So let's go ahead and add those two things. So we can say, let's go ahead and just make this emitter our ground, and then between our collector and ground, we also have that resistor RC. And because our output was defined as at our collector, we can say this voltage is V out here. All right, so now let's figure out our base connections. So off of our base, we have three things. We have this resistor R1, which is going to VCC. We have this resistor R2, which is going to ground. Now remember, our VCC is signal ground, so really we have R1 going to ground and R2 going to ground. So they have the same starting point at the base and the same ending point at signal ground, even though it's different places, but we can say that we have then R1 in parallel with R2. So let's go ahead and add that. So we have something that looks like this, and this is going to be R1 parallel with R2. So then finally, we want to connect our sort of input here. And so remember, we've said this is going to be acting like a short circuit for AC signals. So we just have our RS and our VS connected between our base and ground. So coming back down here then, we're going to have some resistance RS, and then our small signal VS. So this was our RS. And so that RS is just some internal resistance associated with our source. Okay, so let's go ahead and add a couple things here. So this is our IB, so we'll use that in our definition. Let's also go ahead and define an input voltage here. So an input voltage, which is, we can see as I'm defining it, equal to that voltage V pi. And oftentimes we're going to be interested in our input and output resistances as well. And so with that RS being part of our source, we can say that the input to the amplifier is going to be Ri looking in to that terminal there. Similar thing we could do over here, looking in from our output, and we could define some output resistance of the amplifier uppercase R0, not to be confused with our small signal output resistance of the transistor. In this particular case, we're not going to go through the details, but you could find that this is just going to be R0 in parallel with RC. We'll talk about general output resistance later on in the summary table. And what we can see is that our input resistance is just going to be R1 parallel R2 in parallel with R pi. So Ri is that parallel combination of 1 and 2, and then also in parallel with R pi. So the reason we can kind of separate those two sides of the circuit is, of course, we have no connections other than they're both connected to ground at that emitter. Okay, so if we want to then find our small signal voltage gain, what we want to do is find an expression for our output voltage, find an expression for our input voltage, and then relate the two to one another. So on the input side, we can use voltage division to say that that voltage Vin is going to be equal to our Vs times that Ri, our input resistance to the amplifier, divided by Ri plus Rs. And so again, keep in mind that our Ri is basically just saying we have some black box here, so our whole amplifier is just some black box, and we want to replace it with just a single resistance Ri. So that's kind of the idea there, and that's why we can do that voltage division shown below. All right, so let me close this parentheses here. So now looking at the output side, again, we can see that this current is just going to be staying on the output side. It's going to be going up, splitting between our R0 and our RC, so we'll have some going through RC, some going through R0. But what we can say is let's just consider the parallel combination of those two resistors. Then we can define our V out as being negative beta IB times the parallel combination of R out and RC. And again, the negative is because the voltage drop is in this direction. All right, and then finally, as we've said before, that Vin is equal to V pi. So Vin is equal to V pi. And then looking at this diffusion resistance R pi right here, we can see that the V pi is just equal to IB times R pi. So this is equal to IB times R pi. So what we want to do now is just put all of this information together. So of course our small signal voltage gain, A sub V, is going to be equal to output divided by the input. And what we see is when we divide this output by the input, we're going to have this IB term canceling out, and we're going to be left with just a, negative beta times R0 parallel with RC divided by R pi times Ri divided by Ri plus Rs. And so that would be our small signal voltage gain for this circuit. So a couple of things that we can note about this is we see it has a relatively high dependence on some transistor parameters. So that would be a drawback or a con of this system. So drawback is relatively high dependence on our transistor parameters. And so of course the transistor parameters I'm referring to are the beta and the R pi. Our R0 is here as well. Depending on the RC value, that might or might not be as significant, but primarily we're concerned about dependence on the beta as well as our R pi value. And so ideally we would want AV to be completely independent of these component variations. So what we're going to look at in the next video is a way that we can improve our circuit in order to achieve that.